We are going to demonstrate to you all how a healthcare operating system or healthcare IT infrastructure in a hospital looks like, how it should work ideally. So this is the OpenHealthOS kernel we have. Here if you connect a cluster, you can see the different microservices mesh here have opened up. FHIR, registry, validation, LLM, these we have added in the kernel itself. And here you can see the system logs. The connection is established and there's a CDR endpoint. It is ready to receive our admission. Once we receive the admission, it will run the FHIR, of course, which you can see here, the FHIR of the patient. And here is the output of the CDSs or ML, which it has also given reason. Then the platform registry has these ML models: readmission V1 and sepsis V2. We'll see the significance of this later. So now we'll start the streaming from the Internet of Medical Things, Internet of Medical Devices, which we are abstracting hardware. So there's the hardware abstraction layer. As you can see here, you can see the legacy and the optical abstracted drivers values. And now the stream from IoT will soon start. Once that starts, we'll see the readings here. And okay, the stream has ended. Let's start it again. Yeah, now we can see how the stream looks like. It's routing edge sync, and sometimes it skips FHIR for bandwidth optimization. Now we'll simulate a network disconnection. So it says network down, buffering at edge. Once we restore it, it will again start syncing. It will flush the buffer it had stored into the FHIR, and we can see it all here in the FHIR, the batch, and it's how it's going. So the stream session has ended now, and all of this information has gotten pushed into here you can see the latest sync. It has got pushed into the FHIR. Now we'll see how a training model will look like. So once you train plugin, the machine learning model will train itself. Once you plug in a architecture, it will start learning, and it will also do validation. Once that validation is passed, the accuracy, as you can see, is 87.7%. so once that has passed, the new version will get promoted to production. So you can see here now in the platform registry, you can see the sepsis detector. You can also change the model and train it. Again, it will initiate the MLOps pipeline, and in this case it seems that the accuracy is too low or there's bias detected. So now in our platform registry, this model is not come in. I can also compare the models with each other. So in this case, our model diabetes risk model is offline, so we just select another model and train it again. Now it has passed. Now we'll compare A and B. Now you can see that the clinical decision support has updated itself, and you can see the results when you plug in the agentic AI. Here you can see that the risk is now 10%. Since it has accepted the sepsis detector ML model, risk is 10%, and accordingly it will give in the care plan it will give low risk. So this is how the agentic AI is working, and it will write this plan to the FHIR R4. So this is how we can also execute a kernel scheduler stress test, which means if a lot of stress is in the kernel, it will preempt the critical tasks. And this is how we are showing it. All of this is happening in backend, and you can see all the code, but this is how it's supposed to happen. The next thing we'll see is the different terminologies and adapters that we need in healthcare IT. So this HL7 adapter, as you can see, this is the payload. This is how raw HL7 looks like, and this is how our backend has translated into FHIR. And you can also see the zone output here. Now for now I will switch on all the adapters. You can see the payload and you can see the addition of in the FHIR. So it's converting all these raw inputs into FHIR resources. As you can see here, we have added pathology also. So DICOM, SDOH, you can see them updating here also, and then the research. So the last one should be the research. Yeah, you can see here on study research subject, right? So now we will switch on the semantic aligner. Now it has coded everything. So you can see code for semantic code, which is either SNOMED city or Loing code according to the resource, and it has coded all the resources. You can see that the code is aligned, it's semantically aligned. And now if we see the context engine that's produced finally, you can see all these details of the patients, and you can see that the context engine has aligned itself to how it looks like here. You can see the equity, the problems, the care gaps. So this is a care gap, HbA1c is missing, so you'll see it there, and these are all the factors. We can remove all these factors and it will stop showing here. As you can see, genomics, since we removed, it's not showing here. The same thing which we can see it in a canonical mapper, which shows the researcher's point of view. So if you remove the semantic aligner, you can see there's no concept ID, but if you plug it in, you can see that the concept ID is aligned here. And from a research point of view, I will show you one demonstration where if you go to researchers mode, right now you're not seeing anything, but once you start the role-based access, the PCRM policy, you'll see that the genomics is redacted. So the patient, say, has not consented to show his or her genomics, so that's redacted. You can see here, redacted by governance, redacted by PCRM. You can see whether the patient has opted for the consent, and this is audit, so you can log the access event that has been accessed. And in clinician's point of view, this will be different, so the context will differ according to the role of the person accessing it. And you can see the context change here. So most of these has come from our FHIR. You can also see the equity, the problems, and the care gaps, which has changed according to the amount of data that we have plugged in, the adapters that we have plugged in. Right. So this is how the data input, output, ingestion, and a layer of governance in between should ideally work like in healthcare IT.